Here on the South Dakota Mine Steel Bridge team, we focus on innovative design, accuracy of fabrication, and a fast construction speed.
We work together so well, and any problem that comes up, we work together to fix it.
We know what we're doing, we know what we want to do.
Even though we sometimes have disagreements, we always find a way to work together.
Being able to do literally everything that goes into this project. So the design, the fabrication, the building, the strategy.
This bridge has been through a lot.
It's never quit.
We are the loudest, and we get fired up during build, and we're ready to crush it.
This year's bridge design features a substructure on the bridge using trailer hitch connections. We have a three-dimensional deck to help with lateral support. We also have 4 lats across the span of our bridge.
Designing this year's bridge was a bit of a whirlwind.
The rules came out in September, and so we went through and checked and looked for all of the connection rules, and then looked at the bridge envelope that showed us the size and dimensions of the bridge.
We got a very large and open envelope for the bridge, so you could have a superstructure or a substructure. We designed about 40 STAD models in total, not including the ones that had small iterations of different things that were changed in them. And it was mostly just an idea of, will this work or will it not?
We both tried super and substructures. We eventually decided to do a substructure because the superstructure designs weren't quite working with the way that drive had to go over the bridge.
We had a lot of different STAD models, so we took them all, looked at their deflections, looked at their self-weights in STAD, and then started to approximate build times. And once we had build times approximated, we put them all into an Excel spreadsheet that used the scoring algorithm that kind of shows your overall cost and went with the cheapest overall cost.
It's really interesting, the connections we're using this year.
The connections on this year's bridge, we had a mix of 3 different kinds of connections. We had our top stringer connections, which were an inverted V kind of situation, where you had a V connection that slotted into the other side at an angle for building ease. And then we also had some trailer hitches, which we've used in the past, which is just 2 flat tabs surrounding a tube with a bolt going through those.
Fabricating this year's bridge is kind of broken up into 2 parts of fabricating a bridge, testing it, and then fabricating another bridge in a much shorter amount of time.
Our first load test was on March 25th, and that ended up stopping at 1,200 pounds of load because our substructure connections that were the curved surfaces yielded completely. Those connections that were water jetted were 1.5 inches deep, so it caused some aggressive striations into the material in the joints. Our second iteration we did in around 2 weeks. A lot of fabrication. We cut the deck down and added what we call a third dimension to it, which basically just created an equilateral triangle with the top and bottom stringer. And that added some very good lateral rigidity. We also scrapped the entire substructure tubes that we had already constructed because the connections that yielded were so large lengthwise that in order to use the trailer hitch connection that we were hoping for, we had to refabricate all of those tubes.
This year we've done a lot more calculations, connection specific wise. As the student advisor, resident grad student, and someone who's actually taken steel design on the team, that opportunity kind of fell to me. We were analyzing the substructure connections and the bottom of the stringer connections, given that the substructure connections on the 1.0 iteration didn't fare so well. So for the substructure connections, which are a simple trailer hitch style now, we calculated 5 different limit states on the tabbing material and bolts themselves, including shear yield, shear rupture, block shear, bolt bearing, and bolt tear out of the material and on the bolt itself. The controlling limit state for substructure connections had a capacity of 4.2 kips, and when analyzing and taking the stress values that were traveling through that connection from STAD and then finding out how much load was going to be on one of those tabs, we found out that only about 2.5 kips would be present on those tabs, which is significantly under our controlling limit state. We also calculated the same thing for the bottom of the stringer connections. We calculated the same 5 limit state. The controlling limit state for the bottom of the stringer connections, which was 4.2 kips, closer to 4.3 actually. But then calculating the connections moving through the bottom of the stringer tubes, we found that the most one of those connections would be in is 4.2 kips. So we're utilizing almost all the capacity of those connections theoretically.
We fabricated a whole nother bridge in 2 weeks. It was extremely impressive. We were able to load test with expected deflections at the second load test, and we just kept going.
We wanted 4 builders, still kind of want 4 builders, but 6 is just the right option for us. It's faster in aggregate time, and it helps speed things along with being like human lats and holding up other stringers of the bridge. So.